Hello everyone. Today we are going to discuss the problem longest flight route from CSES Graph problem set. Let's go through the problem. Olivi has won a contest and the prize is a free flight trip that can consist of one or more flights through cities. Of course, Olivi wants to choose a trip that has as many cities as possible. Olivi wants to fly from Sirjala to Lamala so that he visits the maximum number of cities. You are given the list of possible flights and you know that there are no directed cyclic cycles in the flight network. So the first input contains two integers n and m, the number of cities and flights. The cities are numbered 1 to n. City 1 is Sirjala and n is Lamala. So Olive wants to go from city 1 to city n. After this, there are m lines describing the flights. Each line has two integers a and b. There is a flight from city A to city B, and each flight is a one-way flight. What you need to output, you need to first print the maximum number of cities on the route. After this, you need to print the cities in order they will be visited. You can print any valid solution. And if there are no solution, that is city n can't be reached from city 1, then you need to simply print impossible. Constraints is number of cities is of the order of 10 power 5, number of flights is of the order of again 10 power 5, and cities are numbered 1 to 1. So let's first of all try to understand what the problem is, and then we can see how we can actually solve this. So I have just copied the input over here in the form of graph. So let's see what the problem actually means. You want to go from city 1 to city 5 by covering maximum number of cities in the route. Now for this particular example, if you look from city 1 to city 5, there are two possible options. Either you cover this path. If you are covering this path, can you tell me the number of cities you are visiting in the path? 3, right? City 1, city 2 and city 5. So if you are covering this particular path, number of cities you are visiting is 3. Similarly, there is one more possible path to cover that you can choose to go from city 1 to 5. That is this particular path. Right? If you are covering this particular path, can you say the number of cities you are visiting? 4, right? City 1, city 3, city 4 and city 5. So there are total 4 cities. Now, since you want to choose a path that contains maximum number of cities, so your answer will be 4. And also you need to print the path. So your path will be 1 to 3, 3 to 4, 4 to 5. So this will be your answer. So I hope the question is clear to each and every one of you. Also, a very important point in the question that is mentioned is that there is no directed acyclic graph. Sorry, there is no cycles in the graph. What kind of graph is this? Then we can say it is a directed acyclic graph, right? DAG. It's very common nomenclature that we give, directed acyclic graph. It is a directed graph and it does not contain a cycle. Okay. Now how we can actually solve this? Now, if you look up to the question, what do we actually want? We want that maximum number of cities to cover to reach city n, right? If it was minimum, we would have solved this problem via Dijkstra, but over here the question says maximum, right? So how we can actually solve this? So to do this, what comes to my mind is, can we use dp over here? I think we can use. What if I define a dp state such that dp of I tells me maximum number of cities visited to reach city I. If I define a dp something like this, such that dp of I means the maximum number of cities visited to reach city I, can I say dp of n will be my answer? Right? And I can also say that dp of 1 will be 1. Can I say these two things? Right? Okay. So we have already defined the state. We have already defined the base cases. how do we actually write the transitions? So for writing the transition, the thing that comes to all of our mind is that, okay, if we have an edge from node U till node V, so I can write that dp of V is equals to maximum of whatever the value of current dp of V is, comma, dp of U plus 1. We all can write this, right? Now for writing this, do you guys agree with me that I should already know what is the value of dp of U? So to write this, dp of U must be known. Do you guys agree? If I don't know what is the value of dp of U, then finding this dp of V, then writing this particular transition equation makes no sense, right? So I should already know what the value of dp of U is. This means that if I have an edge between U and V, then this dp value should be first computed for U and then it should be computed for V. Does it make sense? See, I am not forcing anything till now. How we started? We started by seeing that, okay, we need to find the maximum number of cities to cover to reach N, to reach city N. So I defined a dp, where dp state I indicates that maximum number of cities visited from city 1 to reach city I. Then we saw that, okay, if this is the case, then our answer is going to be dp of N, and dp of 1 becomes equals to 1 because we are starting from city 1. Then we saw that, okay, now we need to write a transition equation and we have edges in the graph, right? So let's suppose we have an edge from U to V. So what does the transition equation becomes? Transition equation becomes the maximum number of cities to reach city V is equals to maximum of whatever the current value is, comma, whatever the value to reach city U plus one extra city you will visit once you reach V, right? If you use this particular edge and reach city V, you're going to cover an extra city V. So dp of U plus 1. Now we saw that, okay, in this particular transition equation, I should already know this value if I want to write this statement. So from this, I came to the conclusion that dp of U must be known. So from this, I came to the conclusion that, okay, dp value should be first computed for U and then V for any U comma V such that there is an edge from U to V. This is understood. Now from this, can you guess the order in which we are going to compute the dp values for the nodes? Can you guess, guys? Yes, I hope many of you guessed it right. We will process nodes in topological order, topologically sorted order. And that's why in the problem they have already given that there is no directed acyclic, there is no directed graphs in the graph, like there is no directed graph. You know that there is no directed cycles in the graph. They have already given that there is no cycle, so it's always possible to compute the topological sorted order for that graph, and hence you can apply dp over there. So the first task becomes to calculate this topological order, and then you will process the nodes in that order. So this is like a very common thing, like this is a very famous topic, dp in DAG. Like when you apply dp in directed acyclic graph, so you will process the nodes in the order of topological sorting. Like it will look something like this. You have a node 0. Let's suppose you are starting from here. Then you compute for this, and then you compute for this. Let's suppose it looks like this. And then you have this. There won't be any graph because this is a DAG. Then you compute for this. So what I want to say is that if I am computing for this particular node dp value, then I should already know the value for this node and this node. and for this node I should know the value for this node. So we follow in topological order. If we calculate the DP, then this thing will be resolved. So this is how we actually solve this problem. Now for this particular problem, if you guys have watched a solution for just before problem as well, which was a direct problem of topological sorting where we were required to topologically sort the graph, I have used a Kahn's algorithm, right? But for this particular problem, just for better visibility and better understanding, I am going to use a simple DFS for calculating the topological sorting. And what I am going to do is I am going to give a bit of context of how I am actually doing that. So like if you guys remember, what was the basic understanding of topological sorting? That if we don't have any incoming edge to a particular node, then we were keeping that node and removing all the edges going to that node, right? That was the basic understanding, isn't it? So what I will do for a simple DFS is, for every node that I take, first of all, I will process all the nodes that go from that particular node. Let's suppose this is a node and all these nodes go from this particular node, right? So first of all, I will process all these nodes and then I will insert this particular node inside my topological sorting. We will see how I am doing that via the code, but high level, this is what the thing will look like. Okay, so let's see the code for better understanding. So I have taken the number of nodes and edges as input, constructed an adjacency list, converting to zero-based indexing, and then adjacency of u.pushback v. It's the directed graph. Then defining the topological sorting vector and a visited vector for this topological sorting. And currently the index is n-1. What is this index? You will see once I call this function. Now for every node, if that node is not visited, I am calling a DFS function with all of these vectors and index value. Okay. Now what I am doing over here is, in this DFS, I have the node, the adjacency list, the visited vector, the topo vector, and the index. Now see, this index is passed by reference, so it's the common value. So first of all, I am marking the node as visited. Okay. Then what I am doing, I am not putting this particular node currently inside my vector. So the insertion will happen from the end. Like see, I will give you an example. Let's suppose this was the thing. This is node 1, this is node 2, and this is node 3. Let's suppose this was the graph I had. So currently my index value is n-1. So basically n value is 3. So currently my index value is 2. Okay. So what I do is, just a minute. Yeah. So currently my index value is 2. So what I do is, I have called DFS with node as 1. So node is 1. So in my visited vector, I marked 1 as true. Okay. Now from this, I will go to all neighbor nodes. So let's suppose I first of all go to node 2. So I will mark node 2 as visited. I will mark node 2 as visited. And I will see that there are no neighbor nodes, right? There is no neighbor nodes. So in my, I already have a topo vector constructed of size n. So at index 2, since the current value of index is 2, so at index 2, I will simply push this particular node 2. At index 2, I simply push this particular node 2 and I will subtract the value of index by 1. So now my index becomes 1. Okay. And I will return. Once I return, now I will call to the next adjacency node. So which is 3. So I called 3, marked 3 as visited, saw that there is no adjacent nodes to 3. So I will now push 3 inside my topo vector. So now the current value of index is 1. So at index 1, I push 3. And I subtract the value of index, so value of index becomes 0. Now I return again, no more adjacency nodes, so at index 0 I simply insert 1. So this is how my topo vector will look like after a simple DFS. So this is how I am doing a topological sorting. For every node I am processing all the adjacent nodes first. Since I am inserting from the back, so I am keep on inserting, and then at the end I insert this particular node. So this makes sure that this particular node is coming before all its dependent nodes. Okay. So this is what I am doing. Marking the node as visited, going over all the adjacency node. If the neighbor is not visited, calling the DFS, and then at that particular, whatever is the index value, at that particular index value, pushing the node and subtracting the value of index by 1. If I am doing this, I will get a topologically sorted vector in topo. Okay. Now we apply DP. So for DP, I have just created a distance vector. This you can name it as DP vector as well, with size as n and initial values as 0. And since you need to find from city 0 to city n-1, basically 1 to n, I have converted it to 0 based indexing. So from city 0 to city n-1. So marking the distance of city 0 as 1. And also, if you remember, in the problem, we need to print the path we are following, right? So I am not going to discuss this now in this particular problem. If you have solved every problem till now in the CSES, you are very much familiar with how do we actually print the graph by maintaining the parent vector, right? So that's what I am doing over here. And initializing every parent of I with I. So this is an inbuilt function iota that marks every index I. You are starting the counter with 0. So it will mark parent of I as I. That is parent of 0 as 0, parent of 1 as 1, like this. Okay. Now let's suppose you had the topological sorting in this particular order. 2, 1, 0, 3, 6, 5, 2. So you have to start from 0, right? So these values are of no use to us because we want to go from city 0 to city n-1. So you have to start from city 0, right? So that's what I am doing over there. I have kept a variable start found as false, going over all the nodes in the topological vector. If the start found is still false, this means that in this vector I have still not got 0. In that case, I am going inside, and if the value of node is 0, then marking the start found as true. Otherwise, simply continuing, because till now I haven't got 0, so these nodes are of no use to me. Okay. If I have got 0, then going over all the adjacency node and a simple transition equation as we have discussed. If distance of node plus 1 is greater than the distance of neighbor, then this is greater than the distance of neighbor, then I am marking the distance of neighbor as distance of node plus 1 and marking the parent of neighbor as node. I would have simply written something like this as well, that distance of neighbor is equals to max of whatever is the value of distance of neighbor, comma, distance of node plus 1, because you are going from node to the neighbor, right? I would have written something like this as well, but since I needed to populate the parent, and when I will populate the parent, when from node to neighbor, you are getting more number of nodes in the path, right? So for that reason, I have written it something like this, that if distance of node plus 1 is greater than the distance of neighbor, in that case, distance of neighbor will definitely become distance of node plus 1 and parent of neighbor will become equals to node. Once you are done with this, if distance of n-1 is still 0, this means that it is impossible to reach from city 0 to city n-1. So simply printing impossible and returning. Otherwise, a very common method of reconstructing the path, since we already have the parent vector, initializing the current node as n-1, while parent of current is not equals to current, in my path, I am simply pushing back current and changing current to parent of current. And at the end, the starting node is still not in my path. So pushing that in my path, and we have the reversed path currently, right? So we will reverse the path to get the correct path. I haven't discussed this thing in depth because we have already covered this in almost 5 to 6 problems before. So I'm expecting you guys already know how do we actually reconstruct the path from the parent vector, or how do we actually print the path by keeping the parent vector and then reconstruct the path using that. Once you're done with this, I'm printing the maximum number of cities from 0 to 1, from city 0 to city n-1, which is stored in distance of n-1, and then also printing the path. Node plus 1 because I'm converting it to 0 from 0 to 1 based indexing. So this is how actually you can solve this problem, a very, very important problem in context to, like, if you didn't know how do we actually apply DP with DAG. So this is a very good starting problem for you to begin with. Okay. I hope all of you guys understood it. Thank you.